now we talk a little about the nature of the spectrum. The spectrum. So what do we want to say here? We want to go back to the Schrödinger equation here and just move one term to the right-hand side and just see what can happen in terms of singularities and discontinuities. So first of all, we always begin with the idea that psi must be continuous. And the reason psi must be continuous is that we don't want singularities worse than delta functions in potentials. If a function is continuous, the derivative might be discontinuous, and the second derivative would have a delta function. So the second derivative would have a delta function. But if the function is not even continuous, the second derivative would have derivatives of delta functions. So somehow the potential would have to have that, and we don't want it. So to simplify our life, we say that psi must be continuous. Now, one second. If psi is continuous, we will consider several possibilities. Possibilities for V. This for V of x. So first possibility, one, V is continuous. So psi is continuous and V is continuous. If psi is continuous and V is continuous, this product is continuous, psi double prime is continuous, and psi prime is continuous. Two, V has finite jumps. Well, if V has finite jumps and psi is continuous, this product has finite jumps. So psi double prime has finite jumps. If psi prime has finite jumps, the worst is that psi prime still must be continuous, but it changes. Psi prime could look like that, could have a corner. But it cannot be worse than that, because if V has finite jumps, if psi double prime has finite jumps, and if psi prime is not continuous, it would have delta functions. So for these two conditions, continuous or even finite jumps, psi prime is still continuous. Things change qualitatively if 3, V has delta functions. If V has a delta function, then psi double prime has a delta function, and psi prime, therefore, jumps. Psi prime is not continuous. Psi prime jumps. This may be reminiscent to you whenever you had to solve the problem of a bound state of a delta function. You got a wave function that looked like this, in which psi prime jumps. And it has to jump because psi double prime has a delta function. Another case in which psi prime jumps is for V has a hard wall. Hard wall. That is, the potential suddenly at one point becomes infinite, and it prevents the particle from moving across. A hard wall is a place, as you remember in the infinite square well, in which the wave function vanishes, but the derivative doesn't vanish. So you could say that psi is 0 here outside. Psi prime then jumps in that it's non-zero here and it's 0 afterwards. So now you could be a little, I don't know, you could object to what I'm saying by explaining that, well, we shouldn't talk about the wave function beyond the hard wall, and in some sense you're right, but suppose we do and we say the wave function is just 0 everywhere, we see that psi prime jumps. So really psi prime jumps. So this is as bad as things can get. So we can summarize this in just one sentence. The sentence reads, psi and psi prime are continuous unless V has delta functions or hard walls, in which case psi prime can have finite jumps. Finite jumps. So basically, psi and psi prime continuous. Exceptions, delta functions and hard walls, and psi prime can change. Now, the next thing we want to do is give you intuition for this incredible result that there's no degeneracies in one-dimensional potentials. That is not to say that the proof is not good enough. It is just to say that we can illustrate that without going into a mathematical proof that is more complicated. So how do we do that? We'll consider the following case, a simple case, an example of a potential of this form. V of x, this is x, and here is V of x. And we will try to find a solution with some energy that is like that. An energy that is right there below the barrier. So this would be a bound state. Why? Because solutions here are exponentials that decay, and here the wave function would be oscillating, presumably. So the wave functions go to 0 and infinity, you could get a bound state. So let's see how we get a bound state. Now, the argument I'm going to follow is just an elaboration of something you can read in Shankar. And it's a nice and simple argument. So we want to understand why we would get here at no degeneracies, and even more. In fact, not just no degeneracies, but the spectrum is quantized. That is, you find one energy and then another energy maybe and another energy. So how do we see that? Well, you look at the way you could write solutions and count the parameters of the solutions and try to see how many conditions you have to satisfy. So here, the wave function would be a decaying exponential. A decaying exponential is of the form alpha e to the k kappa x, because x here is negative. So this decays as x goes to minus infinity if kappa is positive, and that's how a solution looks. You need one coefficient here to determine this solution, so I'll put a 1 here. Now in here the solution is oscillatory, so it's a sines plus cosines, so you need 2 coefficients. In here the solution must again be decaying, and therefore you just need 1 coefficient. Again, this time it would be a beta e to the minus kx. The fact that this potential looks symmetric, I'm not assuming it is. Yes?
Won't one of the coefficients be unconstrained by normalization? Like, isn't one just the normalization factor?
Okay, how about normalization? Indeed, we have 1, 2, and 2 and 1, so a total of 4 coefficients. for parameters. But indeed, suppose you wrote your whole solution. You could say, look, let me divide this solution by 3. That's an equivalent solution. I'm just checking if it solves the Schrödinger equation. That's all I have to check. I don't have to check normalization. Normalization, in fact, is sort of irrelevant here. You just need to know if a bound state exists. So indeed, even though you have these 4 parameters, given that you can multiply the solution by a constant, there's just 3 constants to fix. 4 parameters, and via normalization, or the multiplication by any constant, just 3 constants to fix. But this potential is nice enough that psi and psi prime must be continuous. So you get 2 conditions here and 2 conditions here. So 4 conditions: continuity of psi and psi prime, continuity of psi and psi prime. 4 conditions. So what did we get? We got in trouble. We've shown that this is unsolvable in general because there are more conditions than parameters. Now these equations could be a little peculiar, and maybe this is not completely general, but you seem to have more conditions than parameters. But here comes the catch. The solution really is determined, like kappa. Do you know kappa? Well, you know kappa if you know the energy of the solution. Kappa is determined by the energy of the solution. So some parameters in the solution depend on the energy. So the way we have to think of this is that, in fact, 3 constants to fix, but 4 conditions, so we really need 4 constants to fix, and the 4th constant is the energy. So the energy is the 4th constant to fix, and with 4 conditions, these 3 constants that we had there and the energy, they can just be fixed. So the solution should fix the energy and should fix this coefficient. So the solution exists for some energy, or possibly some values of the energies, but not all values of the energies. So this shows, or at least very clearly illustrates, that you are going to find sets of energies for which you have solutions, depending on how the equations look, and 1 solution each time. So you get what is called a discrete, non-degenerate spectrum. Now, there are more cases to discuss: the case in which you have just a step, or the case in which you have free bound states. And I will not do them, but state the results. Again, all that I don't do explicitly can be found in the notes. So you will look at them later. And so here is the second case: a potential like this and an energy like that, energy level. And what you get here is that, in fact, doing the counting and analyzing the boundary conditions, that you should do it by yourselves, but you will see the answers in the notes. You get here continuous spectrum, non-degenerate. So you will get a solution for every value of the energy. That's to mean continuous spectrum. And 1 solution each time. Finally, this case, if you have an energy like this, E, you get continuous spectrum and doubly degenerate. So two solutions. Now, after this, there's one more result that is qualifies as a theorem, and it is hard to prove rigorously. I will not attempt to prove it here, nor even in the notes. It's hard enough. So this theorem has to do with nodes. Theorem. So if you have the discrete bound state spectrum, discrete bound state spectrum of a one-dimensional potential, and you list the energies, E1 less than E2 less than E3, like that. E1 is the ground state energy, Remember, this spectrum is discrete, so this is less than E2, less than E3, and it goes on like that. The ground state energy. Then you have associated wave functions, energy eigenstate, psi1 of x, psi2 of x, psi3 of x. Here is the theorem. The theorem tells you something about the vanishing of the wave function. It says that psi1 has no nodes, psi2 has one node, psi3 has two nodes, and so it goes so that psi n has n minus 1 nodes. So psi n greater than, well, it's correct. For any n greater or equal to 1 has n minus 1 nodes.